Now here's an interesting question. Take a second to think about this and then look at the answer. Question: how big does a mirror need to be for you to see your whole body? So you've got a person here. They want to look in a mirror, and this person has some height. How big does this mirror need to be? Well, let's think about it. In order for you to see your feet, light needs to be able to go from your feet and bounce off the mirror up to your eyes. Okay, and light needs to go from the top of your head, bounce off the mirror, and go back to your eyes. Now, just from a geometric perspective, we know these angles are the same, which means that the distance from your foot to this normal is the same as the distance from this normal up to your eye, because those angles are the same, and your feet and eyes are basically on the same. We're going to be on the same horizontal location. And the same is true, it's harder to draw with the smaller angle, but the angle of incidence and angle of reflection are the same up here too. And so the distance from your eye to the point of contact with the mirror is the same as the vertical distance from that point of contact to the top of your head. So here, you need to be able to, the mirror needs to extend down to halfway from your eyes to your feet. Here, the mirror needs to extend up to halfway between your eyes and the top of your head. So you've got top of head to your eyes to feet, and half of that. So the answer is that the mirror needs to be half your height in order for you to see your whole body. And, well, it also needs to be as wide as you are. But the height is the key thing. Here's another fun fact. So let's say you have this mirror that is half your height. Now, you might think intuitively that if you're closer to the mirror, you'll be able to see more of yourself, perhaps. Or maybe you don't think that. I don't know. But either way, the light is reflecting up from your toes. It'll hit the mirror halfway up, go to your eyes, and so forth. If you're further away, it's less of an angle, but it has a further distance to go to gain height as it goes off and reflects back to your eyes. So regardless of how close you are to a mirror, you still see the same amount of your body, whether it's your whole body or, if you are at a certain if you're some distance from a mirror and you can see up to the top of your head but only down to your waist, then you get, no matter how close or how far away you get from the mirror, then that's the same amount of your body you'll be able to see. Another way that mirrors are used are what's called a heads-up display, which they use in the military. There's a display that you can see, like in a helicopter, say right on the screen, or right on the windshield of the helicopter, and that's because light is transmitted through the windshield of the helicopter. But there's always, anytime, you go from one medium to another, there's always some transmission and some reflection. So some light will be reflected off that windshield. And so if you've got this windshield and you've got a person here, and there's some sort of dashboard here, there can be a display down here, and the light from that display reflects off the windshield, and the person can see it. And that's what a heads-up display is. It's not actually creating any light or whatever on the windshield. It's reflecting it it's reflecting it from the dashboard. And nowadays they're starting to make screens that actually can project an image, and Google Glasses are one of those things, or those they're starting to show commercials for those flexible screen things. So the technology is coming out now that we could have an actual display that still remains transparent most of the time, but historically they've made heads-up displays just using this principle of reflection. If you have a corner mirror, there will be two sets of reflection going on here. But because of the geometry of the situation, we got normals here, we got a normal here, and all these right triangles, it's sending light out, in and out at the same angle. So if you hit it close enough to the corner, it's essentially going to come back along the the path that it came from. This works in 3D too, so you can picture, what might happen if an angled light ray hit a 3D corner. But this is used. It's kind of interesting. They've set up some of those mirrors from the Apollo missions that actually landed on the moon. They set up some mirrors on the surface of the moon so that you can send a laser pulse to the moon, and the rays will reflect off this corner mirror that they have set up, and then you can sense when it comes back. And they've used that to determine the distance from the Earth to the moon to an accuracy of about 3 centimeters, which, considering the moon is 185,000 kilometers away from Earth, knowing its position to an accuracy of 3 centimeters is pretty incredible. And actually, they've determined that the moon is moving away from Earth at a rate of 3.8 centimeters per year. Although, obviously, again, 3.8 centimeters out of 185,000 kilometers, that isn't too big of a deal, and won't really cause much change in our lifetimes, certainly, but for thousands or even millions of years. Anyway, so that's another little interesting thing. Another important topic is spherical mirrors. Okay, and you can kind of picture this as like a metal ball, I guess you could say, would be a spherical mirror, but generally they're not like a full sphere, but they are part. A spherical mirror is part of a sphere. There are two types. There's convex and concave. And convex is like the outer surface of the sphere. It's like it's bulging toward you. The concave is the inner surface of the sphere. So it's bulging away from you. And those are two types of mirrors that have interesting properties. They're a section of, and these mirrors are a section of a sphere. So let's consider a little bit of terminology here. Let's say we've got our mirror, and this is true for both types. So let's say this is a mirror, and you could be looking at it from this side or from this side, regardless. And say, if I kept going, this would be part of a sphere, but it's only this big. A couple of terms. The center of curvature is perhaps obvious. It is the point that would be the center of the sphere if the mirror was a full sphere. We typically label that point as C for center. Another point of terminology is, there is an imaginary line that runs through the middle of the mirror into the center of curvature is called the principal axis of the mirror. And those are two important terms for mirror.